Welcome to a reading with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 6.1.3. What we just did in the last subsection is we were considering three vectors. So think of these columns right here as vectors. And we wanted to um, perform some isomorphisms, so maps that preserve structure and that are bijective, to view these vectors in another way. And the effect was just to do column operations. Now, at the end of the last subsection, we can think of each column as being the output of something. Like, what if this column right here is like the output of some function g of the standard basis E1, the standard basis element E1, and then here E2, and then here E3, okay? So these are like the images. So this actually makes a map. So the matrix itself that we did out with columns being vectors, you could think of that matrix itself as being a map. And then when we apply when we do row operations, actually what we're doing is we're composing this map with another one after it. So we're like doing an isomorphism after this map. So that's why they were called, row operations were called post isomorphisms. Now we're going to talk about something called pre-isomorphisms. Now, post-isomorphisms were row operations. Pre-isomorphisms are column operations, things done before the map, which should make sense because what do the columns, different columns represent? This column is the image of E1. This column is the image of E2. This column is the image of E3. So if you switch around the columns and things, kind of what you're doing is you're switching around the inputs. So you're like doing something before the map. And the nice thing about G is, written as a matrix, is it's a module map or vector space map, and it preserves operations and outside multiplications and so forth. So if you do outside multiplications in here and do things for columns, just like we did for rows, those actually transfer and go from the inside of G to the outside of G. So things done on the inside actually happen on the outside, and so they end up being regular column operations. So things that were done purely on the inside actually become things done on the outside of G, which could be represented as column operations. So we can put isomorphisms before a map and before a map over here, or after a map over here, and get a good viewpoint. Let's take a look at what we're doing here. So this description just talks about column operations, things that are done before, and then they can pass outward and become columns. So the things that are done with columns are the exact same things you can do with rows. You can switch two columns, you can multiply a column by a number, divide it or something. You can add a multiple of a column to another one. So let's suppose we did all of our row operations to this point, which is what we had in the last little video or last subsection. Then what do? Then we can apply column operations. In fact, what we could do is we could like multiply this column by, well, just +1, and then add it over here. That would make a 0 up there. In fact, that's exactly what's being done right here. And then over here, you could multiply this column by -2 and then add it over to this one, which is what's being done here. So -2 times that column added to that guy, and you get zeros. This is nice. What we've done is we've isomorphically changed. Let's suppose that G was our original matrix, and F is like the row operations, like all the row operation isomorphisms composed together. And then H is all the column operations composed together into one map. And then you have column operations first, then the matrix itself, and then row operations. And what we've noticed is the outcome of this composition is this matrix here. This is a nice one to work with. So you notice that E1 goes to itself, E2 goes to itself, and E3 goes to 0. That's a very simple map. In fact, that's a great map. That actually tells us kind of what the matrix G does. And not only that, it tells us that like what it isomorphically does. So isomorphically, what it really does is it sends everything to something of dimension 2. So which means that the original vectors that we started with put together really only have dimension 2 together. So we can see that right there. Okay. Okay, so we've kind of saw the span, right? It's really just 2, and that we got that directly from this form of the matrix, which is called the Smith normal form. It's done by using row operations and column operations after that in order to get down to something like this, where we have ones going down a diagonal to a point and then zeros elsewhere. This form is unique for each particular matrix. This is so we have a collection of vectors. This is kind of a unique form, which gives us a unique dimension of the span. All right. So we'll end this little subsection right here. Thank you for watching.